In the winter of 1943, high above the gray skies of northern France, the war had reached a deadly rhythm. Every day, the Allied air offensive grew larger, more daring, and more costly. Squadrons of Spitfires and Mustangs streaked through the freezing air, their engines howling as they clawed for altitude. The pilots were young, often barely out of training, and they flew into a sky filled with unseen dangers. But amid the flag bursts and the tracers that cut across the clouds, there was another enemy, one no one had officially acknowledged. It was not the German guns that claimed these men. It was the very glass meant to protect them. At 20,000 feet, when a fighter took a hit, the cockpit canopy, a curved bubble of clear glass, could instantly turn into a weapon. A burst of enemy fire that cracked the surface would send razor-like shards flying inward at impossible speed. Pilots who survived the initial impact often landed their aircraft only to find their faces slashed open or their eyes destroyed. In the chaos of aerial combat, no one thought about the canopy. It was simply there, as invisible as the air itself, until it exploded. The engineers had the reports, they had the photographs. They saw the same grisly pattern repeated in post-flight inspections and medical logs. Small fragments lodged in skin, lacerations deep enough to scar for life. In many cases, the canopy's failure had turned what could have been a survivable encounter into a death sentence. Yet when these findings reached the upper levels of command, they were dismissed as unavoidable consequences of combat. The Air Ministry believed the glass was as strong as it needed to be. They saw no reason to question the standard material. Production schedules were tight, resources were strained. The war machine could not afford to slow down for what they saw as minor technical concerns. But inside the engineering wings of the Royal Aircraft establishment, a few voices began to whisper that something was terribly wrong. At high altitudes, the temperature dropped far below freezing. The canopy glass under constant stress became brittle. When a shell fragment or a stray bullet hit it, even without penetrating fully, it could fracture into hundreds of jagged splinters. The pilots called it glass rain. Some tried to tape the edges of their canopies as a desperate measure, but nothing stopped the sudden burst of flying shards when the glass gave way. In debriefing rooms, pilots recounted the same nightmare: the hit, the flash, the blinding pain as their cockpit filled with glittering debris. Many were pulled from service with permanent vision damage. Some could no longer fly at all. The engineers studying these cases were not frontline heroes. They did not wear flight suits or fire guns. They sat under flickering lamps in quiet offices, surrounded by reports and fragments of broken glass. But they knew what they were looking at: a design flaw hidden in plain sight. The canopy had been designed for clarity and aerodynamics, not survivability. It was made of single-layer tempered glass, chosen for its transparency and ease of manufacture. No one had considered what would happen when that glass was struck by high-velocity debris. The assumption was simple: if the bullet hit, the pilot was done anyway. Why worrying about glass fragments? But that assumption was wrong. Many pilots survived hits to the fuselage or tail. They could return home. The ones who died bleeding out in their cockpits often did so not because their plane was destroyed, but because their faces were. The data was there, test after test, mission after mission. The numbers showed that up to 1 in 4 cockpit injuries came from shattered canopy glass. Yet still, the reports went unanswered. Headquarters was focused on output, on getting more planes into the air, not redesigning those already in production. It was the kind of bureaucratic blindness that wartime often breeds, a refusal to see the small details that cost real lives. To the brass, a cracked canopy was a minor issue. To the men flying through enemy fire, it was a silent killer. In hangars and workshops across England, engineers spoke about it in hushed tones. There had to be a solution, some way to make the glass hold together instead of shattering. Some had read about civilian safety glass used in cars, laminated with layers that absorbed impact. But that was civilian technology, dismissed by military procurement as too experimental and unsuitable for combat conditions. And so the problem remained unsolved. buried beneath a mountain of paperwork and indifference. Yet in those same workshops, one young engineer was not willing to let the matter rest. He would become the unlikely link between desperation and innovation, a quiet figure who looked at the shards of broken canopy glass and saw a chance to change everything. Because while generals fought their wars on paper, Alfred Morgan was about to fight his in glass. In the early months of 1943, as Britain's skies filled with the endless drone of departing bombers, Morgan began collecting data on every recorded canopy failure. He did it quietly, without orders, without permission. He was not looking for glory. He was looking for proof that something as simple as glass could be the difference between a wounded pilot and a dead one. The story of how his idea would be rejected, dismissed, and nearly buried before saving countless lives begins here, with the unseen killer above 20,000 feet. By the dawn of 1944, the air war over Europe had become the defining struggle of the Second World War. The Allies now controlled the skies by sheer numbers, but the price was staggering. Every day, pilots did not return. Every mission came with its own roll call of loss. And yet, within the endless machinery of war, a quiet revolution was taking hold, one that began not in a general's office, but in the mind of a young engineer who had refused to give up. Alfred Morgan's laminated glass, once dismissed as a distraction, had begun to show results that no one could ignore. His unauthorized experiment had sparked a wave of quiet interest. Test pilots whispered about the new canopies that did not shatter. Medical officers noticed fewer facial lacerations and eye injuries in squadrons that had received Morgan's modifications. And in engineering departments across Britain, small groups began conducting their own informal tests. The data kept building, like pressure behind a sealed door. At first, the Air Ministry tried to contain it. They issued vague statements calling for further analysis. They delayed, deflected, and buried reports under piles of bureaucracy. But the evidence refused to stay buried. Every returning aircraft with a cracked yet intact canopy was living proof. The photographs told the story better than any report could. Bullet marks without blood, cracks without casualties. By the spring of that year, the first official inquiry was launched. The results confirmed what Morgan already knew: the laminated glass performed far better under impact conditions than the standard single-layer design. It reduced fragment-related injuries by more than 60%. It resisted shattering under both heat and freezing temperatures. And crucially, it could be produced in quantity without significant delays. What had once been too experimental was now described as essential for pilot survivability. Morgan was called back to London, this time not for reprimand, but for consultation. The same men who had dismissed his reports now asked him how quickly production could be scaled. He spoke carefully, knowing that the victory was fragile. "It is already possible," he said. "The material exists. The process is known. All it requires is the will to act," and this time, they listened. By mid-1944, new Spitfire and Mustang models began rolling off the assembly lines fitted with laminated safety glass canopies. It was not advertised or announced. There were no medals or ceremonies, but those who flew them felt the difference. Pilots returned from missions with stories of bullets glancing off instead of bursting through. One squadron leader wrote in his report, "The new glass has changed the odds. For once, it feels like we are fighting with equipment built to keep us alive, not just airborne." Word spread fast. American engineers at North American Aviation adopted similar technology for their P-51 Mustangs. The change was small enough to go unnoticed in public records, but its effect was immense. Within months, injury rates from canopy fragmentation dropped dramatically. Morgan's laminated glass had turned from a forbidden experiment into a standard of survival. And yet, within the machine of war, recognition rarely followed innovation. The official reports credited improvements in materials technology. Morgan's name appeared only in internal correspondence. But to the pilots who knew the truth, Morgan's glass became a legend spoken of quietly, often over late-night drinks in crowded mess halls. For Morgan himself, the satisfaction was never about fame. It was about seeing the data made real, seeing the numbers turn into lives saved. Each report of a pilot walking away from a shattered but intact canopy was proof that his defiance had been worth it. He often thought of those first to Spitfires, of Flight Lieutenant Clark's words, "Whatever you lot did to it, keep doing it." He had kept doing it, and now others were too. The story of Alfred Morgan's glass shield became, in its own quiet way, a parable of wartime ingenuity, a reminder that not all breakthroughs are born from official orders. Sometimes they come from those who refuse to accept that good enough is enough. His laminated glass was more than an invention. It was a rebellion against complacency, a statement that saving one pilot mattered as much as winning one battle. The true measure of innovation is not how loud it begins, but how long it endures. Morgan's work did not end with the war. After 1945, his methods influenced the development of jet canopies and even spacecraft windows. Laminated safety glass became standard not only in aviation, but in automobiles and architecture. The principle remained the same: layers working together to resist what would otherwise destroy them. In a way, that mirrored the people who built it. Layers of resilience, bonded by necessity, tested by impact. Today, few remember the name Alfred Morgan, but his legacy lives in every pilot who sees through a canopy designed to hold together under fire. His rejected idea outlived the war that almost silenced it. And while his invention never appeared on the front page of newspapers or in victory parades, it did something far greater: it kept men alive to see another dawn. Morgan once wrote in his private notes, "A pilot should not fear the very glass that guards him. If we cannot protect their eyes, we have no right to ask for their courage." Those words, written in the margins of a forgotten report, still echo through the decades. They speak of a truth that outlasts war and bureaucracy alike, that courage is not only found in those who fight, but in those who refuse to stop trying to make the fight survivable. By the end of the war, thousands of aircraft carried Morgan's laminated canopies. Pilots returned home, started families, and built new lives, many unaware that a quiet engineer's defiance had given them that chance. In the great machinery of history, their survival was a footnote, but in human terms, it was everything. And so, the story of Alfred Morgan stands as a testament to the power of persistence, the strength of an idea, and the quiet triumph of one man's refusal to accept defeat, not in the skies, but in the workshop, where glass met courage and turned fragility into strength. By the summer of 1943, the war had entered a brutal rhythm. Allied bombers darkened the skies over occupied Europe, and their fighter escort Spitfires, Mustangs, and Thunderbolts fought swarms of German aircraft in violent, twisting battles high above the clouds. For the men who flew them, survival often came down to inches and seconds. For Alfred Morgan, survival came down to millimeters of glass. He had waited long enough for permission that would never come. Bureaucracy moved too slowly, while men died too quickly. So he made a choice that would have ended most military careers before they began. He was going to break the rules. One evening, when the official lights of Farnborough dimmed and the hum of machines quieted, Morgan and two of his colleagues stayed behind. They rolled back the canvas cover from a crate marked experimental civil aviation materials. Inside were surplus laminated glass panels, unused, forgotten, and technically off-limits for military adaptation. To Morgan, they were the key to saving lives. In a small hangar on the edge of the airfield, they began modifying to Spitfire canopies. Every rivet, every seal had to be adjusted by hand. The laminated panels were fractionally thicker than standard glass, but Morgan's team knew the structure could handle it. They worked in silence, knowing that if discovered, the consequences could be severe loss of position, court-martial, or worse. Yet to them, the moral cost of doing nothing was far greater. When the work was done, two Spitfires stood ready for flight, their new canopies gleaming under the pale light of the hangar lamps. No one outside the small group knew what had been changed. The test pilots assigned to those aircraft were not informed. To them, it was just another mission, another sortie into the deadly blue. The first pilot was Flight Lieutenant Robert "Bobby" Clark, a veteran of the Battle of Britain. He was known for his calm precision under fire, the kind of man who could make impossible landings look routine. When he climbed into his Spitfire that morning, he noticed nothing unusual. The canopy looked clearer, perhaps, but that was hardly remarkable. He took off just after dawn, his aircraft joining a patrol over the English Channel. The mission went as planned until they encountered a group of enemy fighters near Calais. The dogfight was fierce, twisting and diving through the clouds. Clark's Spitfire took several hits. One round grazed the canopy near his head, and for a brief moment, he flinched, expecting the familiar explosion of shards and pain, but it never came. The bullet left a crack across the laminated surface, but the glass held firm. No splinters, no spray of lethal fragments. The canopy remained intact, though scarred as silent shield between life and death. Clark completed his mission and returned to base, landing with his plane pockmarked and battered but whole. When the ground crew examined the damage, they were stunned. The canopy had taken a direct hit that should have shattered it. Instead, it had merely cracked. The engineers crowded around, touching the smooth line where the bullet had struck. Clark, still removing his gloves, laughed softly. "That glass saved my hide," he said. "Whatever you lot did to it, keep doing it." Morgan heard those words from across the hangar and felt his pulse quicken. It had worked. For the first time, the data was no longer theoretical. It had survived combat. He wrote down every observation, measured every impact point, and recorded the stress fractures. The laminated glass had absorbed the bullet's kinetic energy, holding together even at high altitude and sub-zero temperatures. The difference was undeniable. Over the next weeks, word spread quietly among the pilots. They began asking for Morgan's glass. Some believed it was superstition, others called it luck, but those who had seen it in action knew the truth. It made the difference between walking away and never returning. The second modified Spitfire went into service shortly after. Its pilot, squadron leader Andrew Faulkner, was shot at during a mission near the Dutch coast. When his plane returned, the canopy bore 3 distinct impact marks, but no fractures inside the cockpit. Faulkner later told a fellow officer, "I do not know what kind of witchcraft they are putting in these new windscreens, but it is keeping me alive." Still, Morgan remained cautious. He knew when success was not enough. He gathered the flight data, the photographs, and the testimonials. He compiled a full report, meticulous, detailed, impossible to ignore. But even as he prepared to submit it, he hesitated. The experiment had been unauthorized. If discovered too soon, it could all be undone before it began, so he waited. Each new sortie that returned safely added to his quiet confidence. Pilots who had once feared shattered canopies began flying with renewed assurance. Mechanics began asking whether the modification could be applied to other aircraft types. It was spreading one unapproved innovation at a time. Finally, in late autumn, fate forced Morgan's hand. A damaged Spitfire landed at a nearby field, its fuselage riddled with bullet holes. The pilot's commanding officer arrived to inspect it and immediately noticed the canopy scarred but unbroken. When asked how that was possible, the pilot simply replied, "Ask Morgan." It is his glass. Within days, Morgan was summoned to explain himself. The interrogation was stern, the tone severe. He had violated orders, used unapproved materials, and conducted unauthorized field testing. Yet as he presented his data, the room fell silent. There it was in black and white: photographic proof, test results, and combat reports. The laminated glass had performed flawlessly. Injuries that once occurred in nearly every canopy impact had dropped to zero in his modified aircraft. The officials could not deny it. Even the skeptics in the room found themselves unable to argue with the evidence before them. Morgan expected punishment. What he received instead was a cautious nod. The Air Ministry would review his findings for possible implementation. It was not an apology, but it was a beginning. Outside the conference room, one of the officers stopped him. "You were right," he said quietly. "Do not expect them to say it, but you were right." That night, Morgan returned to the workshop and sat beside one of the damaged canopies. The cracks glinted faintly under the overhead lights, a jagged record of defiance and discovery. He thought of the pilots who had come home alive because of it. He thought of the risk, the sleepless nights, and the doubt that had followed him for months. He smiled faintly. For once, the data had won. But the battle was not over yet. The Air Ministry was slow to act, and production lines were still running on outdated materials. Morgan would need to fight again, this time not against indifference, but inertia. Because now the evidence could no longer be ignored. The engineers who once called his idea experimental were about to see how an act of defiance could turn into a revolution of survival. In the quiet workshops of the Royal Aircraft Establishment at Farnborough, a young materials engineer named Alfred Morgan spent his days surrounded by fractured glass, test reports, and wreckage from the skies over Europe. It was early 1943, and the war had turned into a relentless machine that consumed men and metal alike. Yet while the headlines spoke of heroism and victory, Morgan saw something else in the evidence laid before him, a small, preventable tragedy repeated over and over again. He was not a soldier, he did not carry a weapon or step into a cockpit. But he carried with him a deep conviction that science should not be used only to destroy. He believed it could protect. Every few weeks, crash investigators sent pieces of downed aircraft to the research center for study. Most engineers focused on engines, armor plating, or structural damage. Morgan, however, looked for something more subtle, the pattern of fine cracks that spider-webbed across the shattered canopies of recovered Spitfires. Under magnification, those cracks told a story of brittleness and failure. They revealed that the very material meant to shield the pilot from danger became a source of it. The injuries haunted him. Reports described pilots whose faces had been cut so deeply that surgeons struggled to remove embedded fragments. One case told of a man who had survived 3 enemy passes only to be blinded by his own cockpit glass when a stray bullet grazed the canopy. Another spoke of a young lieutenant whose plane returned safely, but whose eyes never saw light again. To Alfred Morgan, these were not isolated incidents. They were the symptoms of a design flaw that command refused to acknowledge. He had an idea, one born not from theory, but from observation. Years earlier, while studying civilian safety standards, he had learned of laminated glass used in automobile windshields. 2 sheets of glass were fused with a thin, transparent resin layer. When struck, it did not shatter into dangerous shards, but held together, absorbing impact energy. The technology was not new, but it had been dismissed by the Air Ministry as impractical for combat aircraft. They said it was too heavy, too expensive, and too untested for war conditions. Still, Morgan could not let it go. He spent his evenings comparing data between civilian and military glass. He simulated bullet impacts using test rigs scavenged from other departments. When a standard fighter canopy panel shattered into hundreds of splinters, he recorded it. When his experimental laminated version merely cracked, but held its form, he smiled grimly and wrote down every result. The more evidence he gathered, the more frustrated he became. The Air Ministry's previous tests had been limited, focusing on clarity and weight rather than pilot safety. They had rejected laminated glass not because it failed to perform, but because it complicated production. To the bureaucracy, any change that slowed output was an enemy of efficiency. But to Morgan, every delay meant another pilot flying with a death trap over his head. He began speaking quietly to his colleagues, engineers who understood the stakes but feared the consequences of defying official orders. Wartime Britain was no place for disobedience. Even suggesting modifications outside authorized parameters could be seen as insubordination, yet a few shared Morgan's conviction. Together, they reviewed mission data, calculating the number of pilots injured by canopy fragments. The numbers were staggering. In some squadrons, over 30% of returning aircraft reported cockpit glass damage. Morgan took the results to his superiors. He laid the documents on the desk of a senior engineer and explained the pattern, his voice steady but urgent. The official barely looked up. "We cannot redesign what is already in production," he said. "We are fighting a war, not conducting a science fair." That sentence burned itself into Morgan's memory. Fighting a war, not conducting a science fair. But what was war if not the sum of thousands of small scientific failures and successes? Every bullet, every engine, every fragment of armor was the result of someone's experiment. Why should glass be any different? In the evenings, long after the others had gone home, Morgan stayed behind. The labs were quiet then, the hum of distant generators the only sound. He tested different resin layers, measuring transparency, heat resistance, and impact tolerance. He discovered that with the right balance, laminated glass could be just as clear as standard panels, and barely heavier. It could save lives without compromising performance, yet he had no authority to implement it. Every attempt to push the idea forward was met with silence or rejection. His reports were filed away, his proposals marked reviewed and not approved, but he kept collecting data. He studied recovered canopies from both sides of the war. German aircraft, he discovered, had begun experimenting with reinforced perspex, an acrylic material that behaved differently from glass under stress. It was another sign that innovation was possible, if only someone dared to pursue it. What drove Morgan was not recognition, but conscience. Each new batch of reports brought news of more wounded pilots. The same types of injuries, the same pattern. It was not the enemy's bullets killing them. It was the fragility of their own machines. He began to write to contacts in the field, test pilots, mechanics, and medical officers. Quietly, they confirmed his suspicions. One letter from a squadron medical officer read, "It is the fragments that do it. The glass acts like shrapnel. We stitch what we can, but it is hopeless for many." That was all the proof he needed. By the end of spring 1943, Morgan had made his decision. If official channels would not authorize a change, he would find another way. He spoke to a few trusted engineers at Farnborough who shared his determination. They began to plan something dangerous, not to themselves, but to their careers. Their idea was simple: modify a handful of fighter canopies using laminated panels salvaged from civilian aircraft, test them without authorization, gather real combat data. If it failed, no one would ever know. If it worked, it could save lives, even if it cost them their positions. Morgan's defiance did not come from arrogance, it came from desperation. He could no longer watch reports pile up while pilots bled in their cockpits. In the dim light of the workshop, surrounded by fragments of broken glass and the faint smell of machine oil, Alfred Morgan made a quiet promise to himself. If the system would not protect the pilots, he would. And in that moment, the engineer who had once been told to forget his science fair became something else entirely. A man ready to risk everything for an idea he believed in. The stage was set for the most dangerous experiment of his career, one that would take place not in a laboratory, but in the skies over war-torn Europe.